You've probably seen a self-driving car gliding down the street and thought it's just following GPS. Like Google Maps, but with a fancier camera. And honestly, that assumption makes sense. GPS is the most visible piece of the technology. But here's the thing, standard GPS is accurate to within about 3 to 5 meters. That's enough to tell you which road you're on. It is absolutely not enough to keep a 2-ton vehicle inside a 3-meter wide lane at highway speed, while a cyclist merges from the right and a toddler runs off the sidewalk. So if GPS isn't doing the heavy lifting, what is? The answer is a layered sensing system so fast, so precise, and so deeply embedded in everyday life that by the end of this video, you won't just understand self-driving cars. You'll realize you've been living inside their logic for years. The fancy GPS assumption isn't just wrong, it's dangerously incomplete. A GPS receiver tells you where you are on a planet. It has no idea of delivery. Driver just flung a car door open into traffic 40 feet ahead. It can't see a faded lane marking or distinguish a crumpled newspaper in the row from a concrete block. Navigation is only a fraction of what a self-driving car must do. The real challenge is perception. Building a live, three-dimensional model of everything within 200 meters of the vehicle, predicting what every object in that model is about to do, and deciding the safest course of action, all within 100 milliseconds. We know exactly what happens when this fails. In the 2004 DARPA Grand Challenge, the first major autonomous vehicle race in history, the world's most advanced self-driving cars were sent down a 142-mile desert course. Every single car failed to finish. The best performer that day made it just 7.4 miles before losing its way. The problem wasn't GPS. The problem was that the cars simply couldn't see. A self-driving car doesn't navigate with one system. It uses 5 running simultaneously, and each one perceives the world in a completely different way. First, cameras. Most self-driving vehicles carry 8 to 12 of them, arranged for full 360-degree coverage. They detect lane markings, read traffic lights and road signs, and identify objects by color and shape. This is the car's color vision, rich in detail, but flat. Cameras alone cannot tell you how far away something is. That's where LiDAR comes in. Short for light detection and ranging, LiDAR fires millions of invisible laser pulses every second in all directions. When those pulses hit a surface and bounce back, the system measures the return time to calculate exact distance, building a live 3-dimensional point cloud of everything within 200 meters at roughly 2.8 million data points per second. Think of it as depth perception that works in total darkness at 60 miles per hour. Third, radar. Where LiDAR is precise, radar is resilient. Radio waves cut through rain, snow, and thick fog, the exact conditions that degrade cameras and LiDAR. Radar measures the speed and distance of moving objects reliably, even in the worst weather. Fourth, ultrasonic sensors cover close range, everything within a few meters, for parking and low-speed maneuvering. All 4 data streams pour into a central AI system running something called sensor fusion. Picture a courtroom. Each sensor is a witness giving testimony about the outside world. The AI is the judge, cross-examining every input, resolving contradictions, and building one single trusted model of reality. From that model, 3 processes run in parallel. Perception, what objects are out there and what are they? Prediction, where are they going? Planning, what should the car do right now? Those decisions flow to the control layer, which commands steering, braking, and acceleration, the full loop. Sense, fuse, perceive, predict, plan, act, completes in under 100 milliseconds. That is 3 times faster than a single human blink. Here is what makes this genuinely staggering. You're already interacting with versions of this exact system every single day. When you unlock your phone with your face, the front sensor fires an infrared projector that maps your face in 3 dimensions, roughly 30,000 individual data points, and an AI matches that map to your stored profile in milliseconds. That is the same depth sensing logic as automotive LiDAR, running on a device in your pocket. When an Amazon package arrives at your door, it was almost certainly moved through a fulfillment warehouse by a robot navigating via simultaneous localization and mapping. The same core algorithm self-driving cars use to track their position against a known map while continuously updating it with new sensor data. When you board a commercial flight, the autopilot fuses GPS inertial measurement units and air data computers to fly the aircraft with more sustained precision than any human pilot could maintain over an 8-hour route. And if your car has adaptive cruise control, standard on most vehicles made in the last 5 years, You are already using a simplified version of the same radar-based detection system at the heart of a full autonomous stack. It reads the distance and speed of the car ahead and adjusts your speed automatically. That is autonomous driving, limited to exactly one dimension. Waymo has logged over 20 million miles of fully autonomous driving on public roads. Tesla's full self-driving onboard computer processes 144 trillion operations per second. These are not prototype numbers from a research lab. This is deployed, at-scale technology operating on the same streets you drive every day. Here's the part no product launch ever shows you. Self-driving systems are extraordinary. It is true within carefully defined conditions. The real world is chaotic in ways that are genuinely hard to pre-program. LiDAR degrades significantly in heavy rain, thick snow, and dense fog, the exact conditions where precise sensing matters most. HD maps, which give these cars centimeter-level lane accuracy, go stale the moment a road is repaved or a construction zone opens. Edge cases, a traffic officer manually directing cars through a flooded intersection, a flock of birds landing mid-road, can completely stall systems trained on tens of millions of miles of normal driving. There's also the ethical dimension. When a collision is unavoidable and the car must make a split-second prioritization, that choice is encoded logic, written by engineers, approved by lawyers, and invisible to the passenger. No company has cleanly resolved this. The systems work extraordinarily well right up until the moment the world stops cooperating. Here's where we land. A self-driving car does not follow. GPS. It rebuilds the world around it from scratch 60 times per second, using lasers, radio waves, cameras, and one of the most powerful AI stacks ever deployed in a consumer vehicle. It perceives, predicts, and plans all before your eye completes a single blink. And you already live inside this technology. It unlocks your phone, flies your plane, and moves packages across warehouses the size of small cities. Next time you see one of these cars on the road, don't think fancy GPS. Think 2.8 million laser pulses per second. Think 144 trillion operations. You'll also a machine can do something that took humans 20 years of instinct, experience, and driving school to learn. The question was never whether these cars can drive. The real question is, are we ready for a world built around machines that can?